Okay, so let me begin by just thanking Eddie and David and other organisers for the opportunity to present work this evening, this morning, whatever your local time is. So I won't repeat, excuse me, the title. Eddie's already introduced that. So just briefly on this slide, an outline of the talk. I'll begin by just describing SHK, something that we've been working on for some time, and the fact that it's a potent Kv1.3 inhibitor, and I'll explain why that's relevant to autoimmune diseases. Then I'll spend actually more of the talk on this scorpion-derived peptide, HSTX1R14A, as our sort of current therapeutic lead, and in particular talk about how we're trying to develop that to treat neuroinflammatory diseases, and as part of those studies to understand its biodistribution, and as I'll show you at the end, the need to develop blood-brain barrier penetrant analogues of this particular peptide. So where this story started for us was some time ago when we solved the structure of SHK. SHK toxin comes from the sea anemone Stichodactyla helianthus, found in the Caribbean. It's a 35 residue peptide cross-linked by 3 disulfide bonds. And when we first solved its structure, it was at the time novel, being based pretty much entirely on helical secondary structure with no beta sheet, which is a common feature of most toxins, most peptide toxins. The target of SHK is the voltage-gated potassium channel. Kv1.3 is what we're interested in, but it actually hits other channels as well. The overall architecture of the Kv channels is as shown here. They're made up of, for the most part, homotetramers of the subunits that look like this, so 6 transmembrane domains, the first 4 of which are involved in voltage sensing, and the last 2, S5, S6, actually go to make up the pore through which the potassium ion travels. So just a schematic based on crystal structures. So here is the S5, S6 region, 4 of them coming together to form a pore through which the potassium ion is going to pass, and these S1 to S4 domains are distributed around the periphery, and they're responsible for voltage sensing. Our peptide, SHK, blocks this channel by occupying the pore, effectively like a cork in a bottle. And it does it very potently. As you can see on this slide, the IC50 for Kv1.3, these are all mammalian channels, is 11 picomolar. I'm just going to have to close that down. Is 11 picomolar, which is fantastic that it's so potent. As it comes out of the sea anemone, however, it's also able to block Kv1.1. Now, Kv1.3 is the therapeutic target that we're interested in. Kv1.1 is involved in nerve transmission, and so one of the drivers in our work on analogues of SHK has been to make selective analogues that only hit Kv1.3 and don't touch Kv1.1 in particular or other channels. And we did a lot of work on that, which I don't have time to cover this evening or today. But that did culminate, and together with people like George Shandy and Christine Beaton and Mike Pennington, culminated in SHK186, which now has the FDA-approved name Dilazotide. And this is the results of phase 1B trial in plaque psoriasis, just with 30 microgram doses twice weekly. And you can see that the benefits of that treatment were quite dramatic. So after 32 days, so these are 2 separate people, the one on the left and the one on the right. So this person's plaque psoriasis on the knee is not totally, but largely resolved. And the person on the left, their hand was stiff, and their skin was so fragile that if they tried to move their hand much, then they often suffered from bleeding. And it's a bit hard to tell in these still photos, but after 32 days, their hand was flexible and their skin had returned to its normal plasticity. So based on those results, the FDA sort of said that the phase 1b trial could be cut short and it could move to phase 2 clinical trials. In the era of COVID, that's, as everybody will appreciate, more difficult. Hospitals are reluctant to start phase 2 trials at the moment. There's also been a change in the commercial partner from Kineata in Seattle to TechV in Columbus, Ohio. But a phase 2 trial is due to start later this year, COVID permitting, of course. So I won't say any more about SHK, but this sort of sets the scene that Kv1.3 inhibition by peptide toxins is a therapeutically viable approach. Moreover, it's safe. There were no adverse findings in the clinical trials. So what I'll focus on for the rest of the talk is an analog that we designed, HSTX1R14A, of this scorpion toxin HSTX1 that occurs in this species of scorpion, which is known as the Asian forest scorpion, or also by these other alternative names. And this was designed on the basis of models of how this peptide docked into the Kv1.3 channel. This was done together with these folk here from University of Sydney. Just to show you what the peptide looks like, it's a 34 amino acid residue peptide. It's C-terminally amidated, and it's cross-linked by these 4-disulfide bonds. And the only change we made in order to improve its selectivity for Kv1.3 over Kv1.1 and everything else was to replace alanine 14, I should say, with arginine 14. You might think, those of you who are familiar with peptide synthesis, that something with 4-disulfide bonds would be a nightmare to refold oxidatively. In fact, quite the opposite's true. It refolds really quickly. It obviously really wants to be in this fold, and once it's in it, it's very stable. Gives a beautiful NMR spectrum. So this is a rigid, fairly rigid structure. Obviously, being cross-linked by those 4-disulfide bonds. Importantly, from the therapeutic standpoint, it's a very potent blocker of Kv1.3 and doesn't really hit other channels at all. So there isn't time to go through all these data, but it's IC50, as you can see here, for Kv1.3. This is all by electrophysiology. Its Kv1.3 IC50 is 45 picomolar, and it has more than 2,000-fold selectivity for Kv1.3 over all other channels. So it's better in that respect than dilazetide. It's about the same potency, but much more selective and much easier to make, I should say. So we're continuing to develop this for a few autoimmune diseases. I won't have time to talk about that today. What I do want to focus on is a rather newer application of Kv1.3 inhibitory peptides, namely to the treatment of neuroinflammatory diseases. So let me just show you in the next couple of slides the rationale for that approach. So microglia, which is the resident macrophages in the central nervous system, look like something like this when they're at rest, when they're not stimulated. And when they become stimulated, they can go through a couple of pathways. Now, this is an oversimplification. People think there are probably more subsets than just M1 and M2, but for the purposes of today's discussion, there's M1, which are pro-inflammatory microglia, and M2, which are anti-inflammatory. And there are times, like during infections, for example, where you want to favor the pro-inflammatory the pro-inflammatory microglia that produce these kinds of cytokines. But there are also times when the M1 macrophages, the microglia, are actually upregulated under conditions where you don't really want them to be. And that is a hallmark of several neuroinflammatory conditions. For example, Alzheimer's, Parkinson's. The data for motor neuron disease are not as compelling yet, but we would also include in that multiple sclerosis, which has got peripheral as well as central aspects to it. And so why is this relevant to Kv1.3? Well, it's because Kv1.3 is upregulated in these pro-inflammatory M1 microglia. So some of the data, these are not our data, these are published data from folks in the US. And you can see here some tissue from Alzheimer's patients. The dark black bars are show the Kv1.3 levels in the diseased tissue as opposed to control. And over here, you've got the corresponding sort of comparison for tissue from Parkinson's disease patients. So Kv1.3 is upregulated, and it turns out, again, from the work of Heike Wolf and Shrikant Rangaraju, that there are some benefits to inhibiting Kv1.3 in these disease conditions. Most of that's been done with a fairly non-selective small molecule. So we've been interested in whether our peptides might have the same beneficial therapeutic effects. So that offers the possibility that our peptide, is potentially able to treat some of these neuroinflammatory conditions typified by an M1 phenotype. And that in turn raises the question of, can these peptides get into the CNS? And so let me just show you a couple of experiments we've been doing to try and probe that question. And one is using PET imaging, positron emission tomography imaging. And so one advantage of HSTX1 is that you can put just about anything at the end terminus of it, and it retains its affinity for and selectivity for Kv1.3. So that's actually an advantage of this peptide over SHK, which is not so readily modified. So that's the sort of experimental setup. So just very, very quickly, some results. So we've used copper 64 on the left-hand side in each of the next 3 slides. Is the copper 64 control, and then the right-hand side is the copper tagged version of our peptide. And basically there's 2 mice in each one, and basically you just look at two alternative views from the top and the bottom in each case. So you can see that after 6 hours, there's huge amounts in the kidney, as you'd expect. You can see down the bottom here the difference between the ones, the amounts that accumulate in the presence of the peptide, the amount of copper that's visible in the presence of the peptide versus when it's not attached to the peptide. So obviously the difference between those is what we're interested in. Let me just go back. The numbers there are obviously higher as well. So after 24 hours, we're looking at smaller numbers, but we still see accumulation in the kidney and a few other tissues as well. After 48 hours, we're seeing, again, the scale smaller, we're seeing hardly any obvious peptide in these animals. But I did want to make a point that even though apparently after 48 hours, the circulating peptides pretty much disappeared, we know from other experiments in a rat model of rheumatoid arthritis that weekly dosing via subcutaneous administration is sufficient to suppress the rheumatoid arthritis. And so I think this is a finding that other people have made with other venom-derived peptides as well, is that there's often a mismatch between the pharmacokinetic half-life, the sort of half-life you measure from these sorts of experiments, or LCMS measurements on plasma samples, and the pharmacodynamic half-life, the actual effective therapeutic half-life, which for the most part is significantly longer. So I just wanted to throw that point in while we had these images in front of us. However, one clear result from these is that there was no brain uptake. These are in healthy animals, I should stress, that there's no brain uptake in these animals. We've probed that with another analog of the peptide. Instead of using PET imaging, we've used fluorescence imaging. And so we created a Cy5 tagged version, again, modified at the N-terminus. This lost a little bit of affinity for Kv1.3, but we've now put a linker, a longer linker, I should say, between the Cy5 and the peptide to restore that affinity for Kv1.3, but it's still subnanomolar. So just to show that this Cy5 tagged peptide does indeed highlight surface expressed Kv1.3. This is work we've done with Yuri Panyi in Hungary. So these are CHO cells overexpressing the GFP tagged Kv1.3, and you can see that there's massive upregulation, and it's inside the cells as well as on the surface here. But the Cy5 tagged peptide is only detecting the surface Kv1.3, so which is what we wanted. And you can see here with the merged image that it's really the surface only that's being labeled by the peptide. So the peptide's doing what we want. It's not being taken up into the cells. And so it's an effective probe of surface expressed Kv1.3. If we don't have any over a GFP Kv1.3 expression, and we don't see any labeling with a Cy5, and importantly also, if we do exactly the same experiments with Kv1.5 as opposed to Kv1.3, we don't see any labeling either. So it is specific, as we would have expected, for Kv1.3. And the reason that's relevant is Kv1.5 is also upregulated in some settings in some microglia and neuroinflammatory conditions. So we want to make sure that our any beneficial effects that we saw were actually being mediated by Kv1.3 and not another channel. And so these support that sort of give us that sort of confidence. Again, however, using in vivo imaging, and I don't have time to show you the results of that, in healthy animals, there was no uptake in the brain. So it's pretty clear that this peptide does not get into the brain when there's no neuroinflammation. However, we have done a couple of different experiments, and I'll just show you one set of data in the interest of time. And this is with an LPS, lipopolysaccharide-induced model of neuroinflammation in mice. And so what we've done is to use not PET imaging, or IVIS imaging, but in order to quantify this, we've actually used LCMS assays. So we've just taken the brain out, done an extract, and corrected for the presence of some residual blood in the extracted brains. And you can see that after about, by an hour post subcutaneous administration, we're seeing actually reasonable levels of peptide in the brain. So what that's suggesting to us is that in a neuroinflammatory model where the blood-brain barrier is known to be compromised, where it's known to become slightly leaky, our peptide is able to get into the brain. So this is quite an exciting result, quite an important result. And so we've also now verified that with PET imaging and the in vivo imaging, the fluorescence imaging system, so that in this model, which is admittedly a crude model of neuroinflammatory conditions like Alzheimer's and Parkinson's, but nonetheless in this model, it's clear that our peptide can get into the brain. Now, the extent of blood-brain barrier disruption in this model is probably greater than the extent in Alzheimer's or Parkinson's, certainly in the early stages of those diseases. So we have seen some beneficial effects of our peptide in a model of Alzheimer's disease in mice, but we're pretty keen to actually enhance the amount of our peptide that gets into the brain, and we would like to be able to use it in a prophylactic setting as well as a therapeutic one. So rather than waiting until the blood-brain barrier has been compromised and become slightly leaky, can we get it in before the neuroinflammation reaches that stage? And so we've been modifying our peptide again at the N-terminus with various peptides which from the literature have been shown to promote blood-brain barrier transport of, in fact, some quite large proteins. So not just peptides, but even quite large proteins. Their uptake into the CNS can be promoted by coupling to these peptides. So we've made those peptides, and we're literally just about to start actually testing those, first of all in an in vitro model of blood-brain barrier transport, which we have in the lab. And then as soon as we have those data, we'll progress to the in vivo models. So that's where that work is up to. There's some promising indications that Kv1.3 inhibition is beneficial in neuroinflammatory conditions. we would like to be able to use our peptide before the neuroinflammation develops. And so our focus at the moment is on these blood-brain barrier penetrant analogs of the peptide. Apologies once again for the disrupted presentation and therefore having to rush a bit. But so let me just finish by acknowledging the people who've been involved in this. So my long-term collaborators have been Mike Pennington, George Shandy, and Christine Beaton, all shown there. The current people who are doing the work that I've presented today are PhD student Sanju, postdoc Dorothy, and one of my colleagues at MIPS, Associate Professor Joe Michelazzo. I mentioned Serdar and Harun as having helped with the design of HSTX1R14A, and those nice fluorescence images you saw have been done in Yuri Pany's lab at University of Debrecen. So I'd like to thank them and thank you for your attention and for your forbearance in putting up with my crappy internet. So thanks very much.